how engineers evaluate and scientists evaluate the change in climate. So that's a little bit different than some of the popular media, because really when it gets down to this, it's really just basic thermodynamics. So if we look at kind of the framing the question on climate change, we can look at what's occurred. So what are temperatures, what are climates, how does that relate to weather patterns like precipitation, snow cover, ice cover. We can look at extreme conditions, and in fact, Earth scientists are looking at those sorts of extreme conditions. So we need to understand what's happening in the present. We can also look back to the past and try and get an understanding of what happened in the past, and then try and predict what's going to happen in the future through developing models that simulate our climate. So an important thing to keep in mind is when we talk about simulating climate, we're talking about something that's fundamentally different than simulating weather. So how many of you believe a weather forecast 10 years in advance? 10 days in advance? Anyone? Iffy, maybe, right? How about 2 days in advance? Yeah, feel pretty good. So the timing, the farther we get in the future, we have more limitations about the variabilities within our model that they can't account for all those variabilities and fluctuations. The same issues we have in climate, but in climate, because we're dealing with long-term averages, we can forecast really well a few years into the future. 10 years is probably, we can do that pretty accurately. When we begin to forecast 50, 100, 200 years into the future, some of these things are averaged well enough that we understand their patterns very well, but some of the things will be based on human behavior. And human behavior is difficult to predict sometimes. So that limits the details of our climate models. So we're going to talk a little bit about how we set up the framework for those climate models. So we see here the effects of some of the changing climate in this picture, where we look at the change in ice cap coverage over the Earth. And the changes that happen on the surface of the Earth are going to be reflected in our models as well. Because as the Earth system changes, as this climate changes, the ice cover changes in the Arctic, that's going to impact our models. And we're going to have variables that are going to change in our models that reflect the change in cover of ice on the surface of the planet, because that changes the mathematics behind our energy balance. So when we talk about our energy balance, okay, we're going to be talking about performing a simple model on the whole planet of the Earth. So while it's a big model, planetary models are big compared to some of the single stream systems or single smokestack models that we've been doing. This is a much bigger model. But because we're averaging over large spaces, okay, we can still get pretty accurate results from this model that can inform us about what's happened in the past. We can calibrate it versus what's happened in the past, and that allows us to come up with some pretty good predictions about the future. So when we look at energy systems, we have to consider whether they have an open or closed system. In our system, we're going to have energy crossing the boundary as light entering our system. Then the energy is going to interact with the mass of our system. There's going to be some energy that leaves that system that's reflected back into space. And we're going to be trying to evaluate the net change of all these things on our system. This is the exact same thing that you do in thermodynamics, right? Your basic thermodynamics class is no different. So whether we're doing this for a golf ball or a planet, the mathematical processes doesn't really change. It's just a matter of the degree of variables that we take into consideration. So the first law tells us that the heat absorbed by our planet is going to be a function of the energy in the system at different states. So our different states in this system, we have an initial state given a certain level of carbon dioxide in the atmosphere. Oftentimes we'll reference that to a couple different dates, perhaps 1990 because of the first Kyoto Protocol, or perhaps prior to the Industrial Revolution, prior to when we began to adding significant quantities of carbon dioxide into the atmosphere. Okay. So we'll have an initial state, and then we'll want to compare what happens when we change the system in some way And the biggest change in our system, I'll show you at the end of the presentation, is the carbon dioxide concentration. And by looking at carbon dioxide concentration solely, we can get a pretty good indication of how this change in energy is affecting the climate on our system. So our basic thermodynamics says that the change in internal energy is going to be related to the mass and the heat capacity associated with that mass of material. Does everybody buy that from basic thermodynamics? So if we change the energy in the system, there's going to be some temperature change associated with that. That's the important bit that you get out of this, and this is the same thing that you would do in a thermodynamics laboratory if you were doing calorimetry. We can do this in a laboratory for different materials, and we can come up with measures for the planet Earth. So we can look at the change in temperature related to the energy stored in the system. And what we're going to be changing, are we going to change the mass of the planet very much? No. But we can change the effective heat capacity of the planet by changing the composition of the atmosphere. So different materials absorb heat differently, right? If you walk on walk barefoot over the summer, and you walk on blacktop, or you have an option of sidewalk or grass, where are you going to walk? On the grass, right? What if the grass isn't an option? You have sidewalk or blacktop. Similar materials, right? Where are you going to walk? Sidewalk. Why? The blacktop will absorb more heat, even though it's a similar material, right? So small changes in materials, changes in reflectivity, has an impact on the amount of heat that's stored within the system. So as we change those things slightly, we can change the heat stored within our system as a function of temperature. So that changes the temperature, the average surface temperature, just like blacktop versus concrete in the summer. Similar materials, but slightly different. So if we think back to that first picture that I showed you, when we go from white cover ice on the Arctic and we change that to blue water, what's going to happen to the planet as we change that? James? The thermal absorption's going to change, so which way? As we get more blue and less white? It's going to increase, right? Just like the blacktop and the concrete, the blacktop's going to absorb more heat. As we decrease ice coverage, we're going to take into account the change in reflectivity of the surface and the likelihood that that blue planet, that blue water, is going to absorb more heat than the white ice did. And in fact, it really does. So that's actually happened. So we're going to take that into account into our models. Okay. So we're going to look at this then as a function of average area of the planet. So we're going to divide the planet up into a simple surface, and we're going to pretend everything's averaged out. So we're going to look at the heat that influences the planet per area surface of the planet. Common way to do this, whether we're doing a thermodynamic experiment for a plate, a cup, or a planet. All the same thing. Okay. We're going to look at the change in temperature from our initial temperature to a final temperature, and then we're going to look at the resistivity. And that resistivity is going to be changing as our climate changes and the composition of the planet changes with regards to ice, water, and other compositions in the atmosphere. That resistivity can change and affect the conductivity. So as we create a model, we're going to look at modeling the light transmission to the planet, because that's going to be our energy input. And we can integrate that over the different wavelengths. So we have this figure here that shows us the penetration of different wavelengths of light. That light is energy. We can transfer that energy or light to energy using the Planck's law to convert that light to energy. And we can define how much energy is going to impact the surface of the planet, including our atmosphere in that. And when we do that, we get a specific energy given a wavelengths of light, the Boltzmann constant, and that's going to inform the temperature of that surface that light is impacting and transferring the energy of the light to the energy of the surface. Okay. These are pretty basic fundamental concepts. So as we look to applying those then to the surface of the Earth, we can pretend that our planet's a black bowling ball floating out into space. No atmosphere, just a black or kind of mottled gray, perhaps, bowling ball floating out into space. So as we do, we can develop a black body temperature for that. And the basic black body equation says that the material is going to give us a constant, the Stefan-Boltzmann constant, the sigma there, that relates the energy to the surface of that bowling ball floating out into space, or whatever environment we do this in. We can do it in a laboratory. Okay? So the temperature is going to be related to the area, the Stefan-Boltzmann constant, which is related to the material, and the energy coming in that's hitting that. Make sense, everyone? And we know from this graph we can measure the incoming energy from the sunlight, from the light that's penetrating and hitting that black body. So we can develop a simple model of the Earth based on those fundamental thermodynamic laws, and that simple model is incredibly accurate as a climate model. So it actually works really, really well as a climate model, and it's based on that first law of thermodynamics, right? It's the first law, so it's pretty fundamental to thermodynamic science. It's not a lot new there. Now, you may have heard in the popular media they talk about fluctuations in solar intensity, and indeed there are some fluctuations in solar intensity. But what we need to realize is that those fluctuations in solar intensity, what percentage are we looking at in terms of fluctuations to like 1 or 2 significant digits? You don't have to calculate it. We're looking at 10%, 30%. What's the variability here over, what have we got, 400 years? 0.1%, maybe. Okay. Not a lot of variability. Okay. So we know that energy coming into the surface of the planet is pretty constant going back over historical values. It goes up and down a little bit. But to 3 significant figures, we can probably use 1370, 1360, 1365, okay, somewhere in that ballpark. So we have a pretty low variation even if we go to those values. We're talking about less than 1% deviation for incoming solar radiation. Now the other thing that we'll take into consideration is the planet truly a black body? Is it going to absorb all the heat? Is it truly black? No. So what we can do is we can come up with a reflectivity, an average reflectivity over the surface of the Earth. And this is based on NASA satellite images which show the average reflectivity of the surface. And because most of it's water, it tends to be associated with the reflectivity of water, which might be around 20%. So what that says is the blue areas, if you look on our blue scale there, are probably around, of the energy coming in, about 20% gets reflected. Does that make sense? So that's what that scale means. If you go to the red side, the red's where the ice is, or was in some cases. Okay? There we have 80% reflectivity. So the ice is going to reflect about 80% of the incoming energy that hits it. It's going to reflect it back into space. So we can come up with an average for our Earth. We just kind of do a weighted average. And we do that, we get about 30% reflectivity of the surface of the Earth. So we're not quite a black bowling ball that's going to absorb all of it. We're kind of a dark gray covered bowling ball. Does that make sense to everyone? So we can come up with a really simple model, and this is about as simple as you can get. Right? So if we put a black body floating out into space with a given radius, we know the radius of the Earth. That hasn't changed much over time. That will allow us to determine the area of that sphere, which was in our thermodynamic equation. We can look at the amount of energy reflected, which we said was about 30%. It's changing a little bit as the ice cover changes. But 30% is good to 2 significant digits. Okay? And then we have incoming solar radiation here at 1365 watts per every square meter of that gray bowling ball. Our average gray, where we put everything together in a mixer, spread it out over the surface of the Earth, so we get this average gray color. Okay? With 1365 watts hitting every square meter of that surface, and 30% of that energy going back into space. Okay? And then we know the Stefan-Boltzmann's constant for that material, for the average Earth makeup. We can come up with that as well. So that gives us a steady state model where we can balance, simple energy balance, the energy coming in that's absorbed from the sun, which is a function of the radius. This is our albedo, or reflectivity. S is our incoming energy. That's the energy that's absorbed from the sun. And over here, this is the energy that's reflected back into space. Sigma is our Stefan-Boltzmann constant, so that's a function of the material, how much heat that material is going to retain, the radius of the Earth, and the effective surface temperature of that black body floating out into space. So when we do that, I said this model was going to be pretty accurate, right? Does this look pretty accurate to you? You think the average surface temperature is about 254 Kelvin? No. Let's put that in something that's a little bit easier to relate to weather. So what is that in degrees Celsius?
Frozen.
Frozen. So how do we get it? 254 minus 273 is equal to minus 19 degrees Kelvin. Okay. Celsius, thank you. Degrees Celsius. Is that an accurate model? What have we not figured in? Brad?
That only half the Earth is hit with sunlight during the day, and there's a tilt.
So actually we kind of averaged that out. I didn't talk about that in the model, but we actually, this model, it's very simple. It does actually account for that. That's a good guess. James? Again, because we average all of that out, so we're averaging this across every square meter, so we're taking into account the variability from the equator to the poles. Again, I didn't go into those details, so that's a really good guess. But these numbers that I've provided for you, the average reflection and the average incoming solar radiation, already account for that. Okay. Is our planet a bowling ball? No. Okay. Give you a hint. It's a bowling ball with a cover on it. Insulation around it. What's our insulation? The atmosphere. Exactly. Okay. So the difference between this minus 19 degrees Celsius and what's actually predicted by our simple model is this greenhouse gas effect. It's our atmosphere. Just like pouring coffee in a coffee mug, a paper cup versus a heavy-duty metal thermos that you might take in your car. You put it in that metal thermos, that coffee's going to be warmer for a lot longer than in a paper cup, right? And it's because of the insulation, you said it over here, the insulation around that coffee. Just like we did not take into account the insulation around our planet, so our average planet surface temperature is about 15 degrees Celsius. So what's the change in temperature due to the greenhouse gas effect? About 34 degrees. So the greenhouse gases add to our atmosphere about 34 degrees Celsius over long periods of time. Okay. So if we have this energy balance, so now we're getting away from those averages and we put this insulation effect into account, we can measure this in. So if we take our 1365 and divide it by the average area and account for that, we get about 341 watts per every square meter hitting the Earth's surface of incoming solar radiation About a third of that from the Earth's albedo, so 109 watts per square meter, is going to be reflected back into space. Never really has a big impact on the surface of the planet. Okay. But remaining here, over here, we get about 161 watts per square meter that penetrates through the atmosphere, is not reflected by the lower atmosphere, and is absorbed by the surface of the Earth. So that's the energy, not really the 1365. That probably wasn't a good number because some of that gets lost in space, actually. Right? Only a portion of that hits the Earth. But when that portion hits the Earth, okay, if it were truly radiating back into space, we'd have 396 watts going back out into space watts per square meter. As it turns out, that doesn't all get back out into space, right? Some of it, only a portion of it, 239 watts per square meter, is actually going to go out into space. So that's the difference of the insulation. Our insulation around the planet is the difference between the 341 coming in and the 239 going back out. The remainder is going to be captured by that insulating blanket, our atmosphere. What captures that are certain greenhouse gases, so certain chemicals within the atmosphere that are going to maintain that. Just like you would rather walk on grass than blacktop because the surface, the soil and the grass don't capture the heat as much as the asphalt does, right? Different chemicals in the atmosphere get to retain that heat in different ways. So the nitrogen and oxygen in the atmosphere, we can have a ton of oxygen in the atmosphere and the energy balance doesn't really care. That's really, really bad absorber of heat. Okay. What about oxygen? That's the next most common gas. You think that's really critical in terms of heat absorption? Not so much. Okay. In terms of heat absorption, really critical to life, right? We don't want to live here on the planet as carbon-based life forms without oxygen. But in terms of this heat greenhouse gas effect, if it were just oxygen and nitrogen on the planet, we would all be a lot hairier and have even thicker beards than Kyle does. Okay. So, if it's not the nitrogen and the oxygen, what's the next most common gas in the atmosphere? This is the hard one nobody remembers. Argon. Okay. Does it absorb much heat? Not so much in proportion. Well, now, what's the next most common gas in our atmosphere? This could be a trick question. What's that? No? 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 It's a gas. We utilize it every day as living beings. I already said oxygen. When we breathe oxygen in, CO2 comes out. Okay? In terms of permanent gases in the atmosphere, carbon dioxide is the next most common gas in the atmosphere, number 4. Okay? So the first 3 don't have a big impact on this number, the greenhouse gas factor. That next one, carbon dioxide, that's our big insulator. The other one is water vapor. Okay? Water vapor can be, dependent upon the day, okay, higher or lower in the atmosphere. That can also have a big impact on concentrations in the atmosphere. So the greenhouse gases are going to deviate how much the Earth radiates back into space. They're going to capture some of that 390 watts per square meter that's radiated back. The greenhouse gases are going to absorb about 350 watts of that energy and then redirect that. Of that energy, some of it's going to be reflected into space, but part of that energy is going to be reflected back into the surface. So it's actually our atmosphere acts as a heat blanket, also adding energy to the surface of the planet, which increases the temperature of the surface of the planet. These things are well known. They've been going on for billions of years. Okay? These things are not really variables that are going to change, and we can't change the chemical nature of an individual element, nitrogen or oxygen or carbon. Those things are going to have heat properties, heat absorption properties that are specific to that element and compound. So if we look at this, we see energy come into the Earth that hits the planet through the solar window. Okay? So that wavelength of energy is going to transfer of light from the space hit our planet. Then that energy is going to bounce off of our planet, some of it, or be radiated from our planet and try and get back out into space. As it does, a lot of that energy is going to pass through this atmospheric window. That's going to allow the energy that's absorbed on the planet, that's captured on our bowling ball, and radiating back into space to equalize that energy balance. It's going to pass through that atmospheric window. But what do we see on either side of that atmospheric window? What are the chemicals up there? Water and CO2. The next most common gases in our atmosphere are going to act on either side of that. They're going to absorb the energy in these wavelengths here. So oxygen is going to absorb some in the very, very ultraviolet range, okay, but that's actually going to prevent a lot of that energy from hitting the Earth. So that's going to be absorbed up high in the stratosphere before it hits the Earth. In terms of the energy reflected, it's going to be that carbon dioxide and water vapor that are the predominant species that hold on to the energy in the planet. Where does the carbon dioxide come from? Okay. Living things, fossil fuel emissions. Okay. What does fossil fuel mean? So have you thought about that? You probably have a little bit, heard it. Fossil fuel is compressed carbon, and it's called fossil fuel because it came from ancient life forms. So if we go back on the surface of the planet, when the planet used to have a lot more carbon dioxide, okay, in chapter 2 of your textbook, there's an illustration of the ancient atmosphere compared to the present atmosphere. The ancient atmosphere used to be dominated by carbon dioxide before all these bloody living things evolved. Okay? As living things evolved, okay, they actually changed the whole composition of the atmosphere. As they changed that composition by sucking up all the carbon dioxide, so we created these algae, these huge floating flats and mats of algae on the surface of the planet that began to suck up out of the atmosphere all this carbon dioxide. Through what process? Plants do photosynthesis, right? So they take carbon dioxide out of the atmosphere and they produce what? Oxygen. Those bloody things changed the climate. They created a huge global cooling event. Why? Because they took carbon dioxide out of the atmosphere and replaced it with oxygen. If it weren't, we'd probably all be much tanner and having beach houses along the northern coast of Canada. There's a whole lot of that, right? But all those bloody plants also created oxygen, so maybe it wasn't a bad trade. Okay? But they totally, fundamentally changed the atmosphere. The ancient plants changed the atmosphere from being predominated by carbon dioxide to being predominated in comparison by oxygen. Okay? Eventually, over billions of years, it leveled out to approximately the levels that we have now, about 21% oxygen and only a few parts per million of carbon dioxide, down to about, prior to the industrial age, about 280 parts per million of carbon dioxide. Where are we now? Not at 500 yet. We're approaching 400. Okay? Right today, probably about 394 to 396. It varies seasonally. There'll be a little graph of that in some of the videos that you can watch online. Okay? So we're in the process of just about doubling the carbon dioxide. And as we do, okay, we change the radiative forcing. That radiative forcing is saying that's the amount of heat that is captured by the atmosphere. All right. So as we look at all the possible variables that have been explored here that change the radiative forcing in the atmosphere, so we know things like methane are also a greenhouse gas. Chlorofluorocarbons that are a result of being phased out by the Montreal Protocol because they were used as insulators. Why? Because they're really good insulators. Really, really good insulators. That's why they were used. When they get in the atmosphere, they're really, really good insulators. We're phasing those out. So in proportion to the carbon dioxide, they have less of an impact on this temperature change, this delta T, due to the greenhouse effect, than carbon dioxide up here on our graph. Now also, there are things like water vapor. As we get warmer, we probably get more evaporation of water. That evaporation of water can turn into what in the atmosphere? Clouds. Yeah, that was an easy question. Right. So clouds are what color usually? White. Does reflect or absorb heat? Reflect heat. So we see here that there's some cloud effect, that there's a pretty good deal of uncertainty about what happens with water or vapor in the atmosphere. If it stays in the vapor form and doesn't form clouds, okay, if we get enough cloud buildup in the atmosphere, it's going to create some cooling. But if it's just water vapor in the atmosphere, it's going to create some heating. And clouds are dynamic. They change a lot, right? They're not constant. Coming up with a good average is hard. So there's a lot of uncertainty with that compared to all the other things. But on the whole, we think that the formation of clouds will actually change the reflectiveness of the planet as we go through climate change. We get more clouds. That will be more white, reducing the absorption of the surface of the planet, increasing reflectivity, resulted in global cooling. If we just had cloud increase. But how does that compare to everything on the other side of the graph? Not very favorably, right? It's not equal. There's more on the right-hand side of the graph than on the left-hand side of the graph. And when it's all summed together, we get this total net down here on the yellow. Okay? The total net change. And what's that pretty close to? If we had to pick one variable to model our climate system of all these variables listed here, and there are more embedded in these terms that aren't really discussed on this graph, but if we just looked at the one variable and said we wanted to look at one thing that was changing in our system that would reflect pretty closely what happens with a more complicated, all these other variables, what will we pick? The carbon dioxide, right? So that top green line for carbon dioxide, it doesn't exactly match that yellow line on the bottom, but it's actually pretty darn close in terms of the variability. It's within the variability, certainly, of that yellow line on the bottom of the graph. So while there are lots of different things happening in our atmosphere, okay, there's some really neat little cartoons that NPR did. I'll ask you to look at those offline that say it's all about carbon. Okay? It really is all about carbon. Okay? What it boils down to, when we look at all these other things in our atmosphere, it's really about the change in carbon dioxide conditions. And when we do that, we put that into a basic thermodynamic model that says what was the carbon dioxide concentration, the radiative forcing, and here they give a time period between 1860 and 2000. Okay. And how will that change going into the future? When the carbon dioxide doubles, when we get about 560 or so parts per million of carbon dioxide, and you will probably see that day in your lifetime, hopefully I live that long, will change the radiative forcing from about 1.56 watts per square meter to 4.28 watts per square meter. That's a simple term, U1 and U2, change in energy within the system. Does that make sense? Basic, fundamental first law of thermodynamics says that when we change that in the system, the temperature of the planet on average is going to heat up. Basic, fundamental thermodynamics. And we can come up with a real good estimate of what that is based on how carbon dioxide changes in the atmosphere over time. And that change is going to be related then to the activities of how we consume those fossil fuels. When we had those big mats of algae, those ancient plants die, suck all that carbon out of the atmosphere, they got buried, become fossilized, became our fossil fuels. They took that carbon out of the atmosphere, buried it in the ground. We're taking it out of the ground, putting it back into the atmosphere. Okay? This is not anything surprising that when we put that carbon dioxide back into the atmosphere, we get a climate that's going to be closer to the climate, okay, that we had when those ancient plants were thriving on the planet in a very high carbon dioxide concentration. Okay? Pretty fundamental. So our current models, and you can go through this in the book, it shows the detail of those models, but they take into account all these potential variables. There's a whole list. You can see how they break up the planet into individual squares that are on the order of 50 kilometers in basis and model the entire surface of the planet based on this to still find what we basically just said, that if we look at carbon dioxide change, we can come up with a pretty darn accurate prediction of what's going to happen to the temperature of the planet based on the carbon dioxide in the atmosphere. So when we do that, this is very similar to what we've done in class, right? We can calculate emissions. When we calculate emissions, we can look at the change in concentration of those greenhouse gases, particularly carbon dioxide, in the atmosphere. Based on that carbon dioxide in the atmosphere and a simple thermodynamic energy balance, we can come up with a change in the radiative forcing in the atmosphere. That change in radiative forcing then leads to a response, a change in temperature of the planet. Changing the temperature of the planet then changes their climate, and the climate responds by more extreme weather events, by other things, melting ice, higher sea level, and other results of climate change. But the fundamental basis, the fundamental model is basic thermodynamics, and that really doesn't change. Any questions? So next time we'll look at, now that we know what's going to happen, we continue to put carbon dioxide into the atmosphere, how do we approach that as engineers? How does that factor into the engineering that you all will do in your lifetimes as we think about mitigation and response to climate change and building resilient infrastructure? Thanks for your time. See you next time.